Okay, dear students, today is our last lecture of this course, Steel Structures, and the final topic is design of beam of flexure members. Okay, you know that beam is essentially a flexure member, and it actually resists the load in the form of flexure or moment. In RC beam, we have reinforcement at the top and as well as in the bottom, and we call it doubly reinforced beam. And we also provide some shear reinforcement at the extreme edges to resist the shear load in shear. In steel structures, however, we can have uh, fabricated W sections. Mostly we use W sections. W section from the manual you can see. Unlike plate girders where we built up that section on our own, we use long flanges, long webs, and actually it has to support a deck, whole deck of a bridge. Whereas in building, we usually use prefabricated W sections, and most of them are given in the manual. But the principle is same. It has to resist the load in form of flexure. The most important thing is that the most important parameter on which a beam is designed is elastic section modulus. So this is Z, represented by Z, and there is another term called plastic section modulus, and plastic section modulus is represented by S. I mean, this is very important parameter, and we would be interested in this parameter, and we'll be designing the beam on this important parameter. It is simple. The Z is actually obtained by dividing moment of inertia or second moment of area by neutral axis, or simply C. So its unit is cubic inches, inch cube, not cubic inches. Sorry. So let's first solve a question, and we are given a very simple question. The thing is, we have to select a W section, and this W section is subjected to some load, and this service load, affected load, is given. It is 48 kips. You should know, I mean, for designing a beam, you should be drawing its shear force and bending moment diagram. A bending moment diagram is very important. And for point load, the bending moment is essentially a 1 degree curve like this, and the magnitude would be simply equal to PL by 4. It's very simple because it is resting at the center. And what if it was subjected to UDL load? Then, for example, I have a UDL here, 2 kip per foot, then, and it is 10 feet. Then the bending moment diagram would be a 2 degree curve with the maximum value of WL square by 8. So this formula would be used to design a beam, and you can solve it. I mean, it has the unit of moment. You know, Fy, unit of Fy is KSI, and unit of Z is inch cube. So we get kip inch, which is a unit of moment. So it's very easy. Using the basic, using the moment diagram, I know that the extreme or greatest moment to which this beam is subjected to is 2880 kpinch. Now, using this simple equation, and we know the properties of Fy, I mean, we know the value for A992 steel, Fy is 50 ksi. So I'm able to compute the value of Z. Now Z comes out to be 64 inch cube. So I'll have to go to manual to select the appropriate section. I have solved it. So I'll go to manual directly, and I have uh, pointed out that page. So I need the value of Zx, that should be greater than 64 inch cube. So here I have 64 inch cube for W16 into 36. So it is I mean exactly the same, but I should be going a bit higher. So therefore I'm selecting this value. The ZX is 66.5 for W18 into 35. So I'll simply say that I'll select W18 into 35 for this question. So I haven't written here, but it is W18 into 35. And this is weight, pound per feet. And this is the length in inches, depth in inches. This question is simple and would be solved by you. Now next question is much detailed question. And the flexure member, the beam is designed in the same way as a plate girder. We have some requirements and you should be very well acquainted with this diagram. And you know this is lambda r and this is lambda p and this is lambda r and this whole is slenderness ratio, and you have to find the slenderness ratio of web and flanges, and you have to decide, and you point out the location of slenderness ratio where it is here, which is non-cylinder or non-compact zone. Here it is compact and here it is slender. So based on your assessment from this diagram, you use the appropriate value for your design. So these are the compactness criteria for flange and web. So it was very different for columns and very different for plate girders. The values may differ. For example, I remember lambda r for column is 4.71 E by Fy, lambda r, and no lambda p there, I remember. So you have the notes and you can go back and go through the same lectures. These formulas, I mean, this is very same for everything. I mean, this is lambda w for web, this is lambda f because this is the slenderness ratio of the flange. Lambda p is the lower bound value, lambda r is the higher bound value, so it should always be greater than this. You need not remember these formulae because it is given here, it's given in the code, it's given in the formula. All you have to do is to know where to use these formula and how to use this formula. Okay, I have this section W16 into 31. I have A992 steel, it means this Fy is 50 KSI. And span length, I mean, if I draw the section of this beam, so it is 30 feet and it has some load on it, and that load is dead load, live load, and self weight of the beam. And you should assume that these loads are UDL because you are not given any point load, and you should know that dead load and live loads are distributed uniformly on the span of the beam. So I have to check the compactness of a flange first, because flange is the first component of a W section or beam which is subjected to moment or loads. So I have to check the compactness or slenderness. These are one and the same thing. So I have to check the slenderness or compactness of this web. So definitely, you know this is BF and you know this is TF, and the slenderness ratio of flange is given by this formula BF by 2TF. So all you have to do is to go to manual and search for W16 into 31, find BF and then TF and find this lambda F value. So I'll go back to manual and I must remember that this is 16 into 31, 16 into 31, W16 into 31. So I have bookmarked it. It is 27 page. 27 page, 16 into 31, this one, right? Area is given, depth is given, but I'm interested in its compactness of its flange. You can find the BF value from this value, 5.53. TF is given 0.440. Divide this value divided by 2 times this value, or you can go downwards and find go downwards. I mean, this is 1 2 3 16 into 31, first in the third section. Okay, 1 2 and this is BF by 2TF value is given, and it is comes out to be 6.28. So you can avoid that calculation and you can simply take the value from here, because it is compact section criteria or compactness of the flange, BF by 2TF. Similarly, compactness of web is also given, or slenderness of web is also given. It is 51.6. I am interested here, 6.28. So it is 6.28. In fact, it is 6.28. This one, right? Now, now my job is to find these values, lambda p and lambda r. And I calculated lambda p from the formula, this formula. Lambda r would be calculated from this formula. My lambda p is 9.15. My lambda r, which is also calculated, but I don't need to calculate lambda r. Why? Because lambda of f, lambda of flange, slenderness ratio of flange is 6.28. So it is well decided that I am here, because lambda p is 9.15, lambda f is 6.28, which is lesser than 9.15. It means I am here in this zone, which is compact zone. The flange is compact. So one of requirement has been fulfilled. My flange is compact. So I'll simply compute the moment, assuming that my beam is subjected to UDL. Now, so I'll calculate first of all factored load using this formula: 1.2 dead load, 1.6 live load. In the dead load, this is self weight, and it is assumed to be a dead load. This is live load, and it is 1.46 running foot, kip per running foot. And I'll calculate, because it is UDL, it is 1.46 kip per foot. And you know, a UDL forms a 2-degree curve, and the maximum point is WL square by 8. So here it is WL square by 8, and it comes out to be 164 kip foot. My flange is compact, so I'll use this simple formula. From the manual, I have this value 54 for W16 into 31. W16 into 31. W16 into 31. Z value should be here 54. This is 54, right? Z value. W16 into 31, right? So 54, right? 16 into 30, 54. And finally, my question is solved. My final answer would be, it is, yes, it is 225 kip foot. So the moment capacity has been found out using this formula. This is the moment capacity. This is the moment to which my beam is subjected to. This is the moment capacity of my beam section, that is 6W16 into 31. Now obviously this 225 is far greater than this, and also I can reduce it using multiplying with factor of safety, multiplying it with resistance factor 0.9, or divided by 1.67, because I am using the factored load. I am using this resistance factor 5. This is solved using LRFT approach. So if you have to solve it using AST approach, so simply you will have to add up dead load and live load, and based on this WU, dead load, and you have to find the MU value, and that MU would be found. I mean, it would be some value, and that would be compared with same 225 divided by factor of safety, and it is 1.67. The thing is, I have solved it using LRFT. Why LRFT? Because I have used the factored load. If I am not using the factored load, then this would be like this. Some value would be here, and it would be much lesser than 164. For example, it is 130 kip foot. and this would remain same, 224, 225 divided by some value that is 1.67, and it would come nearly, I mean, you can compute it. I don't have the calculator. Yeah, I have the calculator. 225 divided by 1.67, 225 divided by 1.67 comes out to be 134. 134. It is again much, I mean, greater than this, so my section is adequate. So you can solve it using AST or LRFT. It's up to you, and it's very easy. Okay, next question is similar to this, and now I have a new section, that is W6 into 15. Bracing length is given, okay, because length is 10 feet, and maybe there are some UDL or UVL, or nature of load is different. That's why bracing is also provided here. Bracing is provided at the length of 5 feet. I mean, it's total of 10 feet, and bracing LB is provided at 5 feet. So I don't know whatever the reason is, but bracing is provided. It is braced. This section is braced, and as again you will assume that your section is subjected to UDL, that is uniformly distributed load. The thing is, the first criteria is to check the compactness of the flange, and this is W6 into 15. You will go to manual. The criteria for flange compactness is same, 0.38 as given in the table, and this is lambda R, 1 time this. So this is lambda R, and this is lambda R, and this is your lambda P. This is 9.15, and this is 24.1, and your lambda F comes out to be 11.5. So you are here, this region. You know, this is slender region, this is compact region, and this is subcompact or subslender region, or non-slender or non-compact, you can also call it, because its value is intermediate between lambda P and lambda R. So it's very easy. 11.5 has been found out from the manual. So I'll again go to manual, and I have bookmarked that page. It is 33 there. Yes, 33, and I have forgot the section. The section is 6 into 15. 6 into 15, W6 into 15, this one, 6 into 15. Yeah, this one. So this 11.5. This 11.5 is the value for compactness of flange. This compact section criteria for flange is 11.5. And this is 21.6. This is the slenderness ratio of flange. In other words, it is the slenderness ratio of the flange. This is the slenderness ratio of the web. For which section? W6 into 15. It is 11.5 and 21.6. I am interested here. 11.5. So, okay, 11.5. Or you can easily find out by finding BF and TF value, and it's very easy. Okay, the flange is subcompact. It is not compact. It is not compact, but it is not slender as well. Okay, next case is to check the web compactness, and it has been found out from the manual. I have just found out. And in the previous section, in the previous question, my job was done very easily because the flange was compact, so I need not do any other calculations. Here I have checked that my flange is not compact, and then I move on to check the compactness or slenderness of web. And again, using the same table, lambda P and lambda R. Lambda P value for the web is 91, lambda R value is 138, and this compactness or slenderness of the web is 21.6. It means my web is compact. I am here. So I am here, As the flange is non-compact, but your web is compact, so I'll use this simple formula. And this is a problem, but because my flange is not compact, so I'll simply use this formula. This is from again the this is again from the manual, 10.8, for W6 into 15. W6 into 15. W6 into 15, this one. Mm-hmm. This so that z value has to be found out. This z value 10.8. Section modulus is 10.8. Fy is 50, obviously, you know, for A992. This is 10.8. Zx 10.8. Section modulus is 9 point. This is elastic section modulus, and then this is again from the manual. This as section modulus, this is elastic section modulus. This is plastic section modulus. 9.72. So both are given in the same box. So everything is from the manual. I am not doing from my own. It's very easy. And lambda p, this lambda value and lambda p values are for the flanges. This is lambda r value for flange. This is actually lambda f, right? And you are able to calculate this moment. And again, this is the bracing requirement, and this has been done. This is same for plate girder. You use this formula to find the lateral torsional buckling, so it is adequate. You will be finding it because it's very easy. Okay, the final ultimate moment comes out to be, because my Zx was 10.8 for this section, it comes out to be 540 inch kips, and which is 45 kip foot, which is again it is okay. This is very important. This is very important. This is the moment which my W section is able to resist, and this value is actually yes, this is the value, or this is the value to which, I mean, which my W section W6 into 15 can really resist. This is the value. This is the value of moment which my W6 into 15 can resist. However, this is the moment to which my beam is subjected to. So my beam is adequate. So I think this is wrong. You will be using this value. I mean, my beam is adequate, right? My section is adequate, so this moment is okay. And again, the moment has been reduced to 38.2 or 5.4 kip foot. So I can comfortably state that W6 into 15 can actually resist, or is adequate in flexure. A flexure, this is a flexure produced by load to which it is subjected to. So I think the statement was, there's no statement, but I have to find the nominal moment, I have to find the design moment, I have to find the allowable. So nominal moment to which my section was subjected to was 42.4 kip foot. So you can again multiply it with 0.9 and divide it by 1.67 to find the value of AST moment and LFT moment. However, this is the moment by which my W section 6 into 15 can resist. Okay, uh, with this numericals, I mean these two numericals, three numericals, rather four. The fourth one would be solved by you. It's very easy. We come to the end of this course, steel structures. I hope it was a good experience for you because you were able to. I hope you were able to understand that. And finally, we have a final term exam, and that exam would be I'm going to post it now because you should have adequate time to solve it by 3rd or 4th of August, because the final exam has to be finalized by 7th of August. And definitely we have gonna have educations as well, so you would be busy as well. So that's why I'm going to post it now. And this lecture is also being going to be posted now, not on Thursdays, because it would be too late for you. And I want you to give much time. I want you to give much time to this steel structure final project or final exam, because it would be tougher. It's not easy because the final exam is actually based on some assumptions, and you have to assume all the sections, W sections, dimensions, so that in order to avoid the plagiarism and copying culture, I have devised the final exam that is quite intuitive, and it would be unique for everyone. So I hope you would be able to solve it, and inshallah I'll try my best to give good grades. All you have to do is put little effort and independent effort. So I wish you all the best luck in future, and I hope inshallah you would be graduating this semester. And always remember me in your prayers. Thank you.